Welcome to The Explainer. Today, we're taking a deep dive into the hidden mechanics of database internals. Okay, let's dive right into this because understanding how databases stay perfectly correct under massive pressure is, well, it's basically the secret to mastering system design.
I want you to imagine a really relatable scenario. What actually happens when two users try to update the exact same piece of data at the exact same millisecond? Say two people are trying to buy the absolute last concert ticket online, or maybe they're simultaneously withdrawing money from a joint bank account. If a database doesn't have incredibly strict rules in place, this simultaneous access literally leads to absolute chaos. We're talking lost money, double-booked seats, and just completely inconsistent data across the board.
And this brilliantly illustrates the heart of our problem. When multiple operations execute concurrently without any sort of control, their steps just interleave in these unpredictable, messy ways. Ideally, we'd want the absolute safety of a serial schedule where one process finishes completely before the next one even begins. But here's the catch, right? Running everything sequentially like that would absolutely destroy a modern application's performance. It's just not feasible. So, to solve this, we have to introduce the true hero of our system design story, the transaction. A transaction is defined as an indivisible logical unit of work. It essentially takes multiple operations, like a whole series of reads and writes, and bundles them together as a single step. The golden rule of a transaction is that it's all or nothing. It either fully commits, making all its changes permanently visible to the rest of the system, or it completely aborts and rolls back, basically pretending those operations never happened at all.
To guarantee this all-or-nothing behavior, databases rely on the famous ACID properties. Let's briefly walk through this critical checklist. Atomicity means all steps execute successfully, or literally none of them do. Consistency ensures the database moves from one valid state to another valid state. Now, interestingly, consistency is actually an application-specific guarantee controlled by your business logic, whereas the database itself strictly enforces the rest. Then we have isolation, which ensures transactions run without interference, as if they were entirely alone in the system. And finally, durability. This guarantees that once a commit happens, those changes will survive power outages, hardware failures, basically any system crash.
Part 1. The complication, data anomalies, and isolation.
Let's see how this builds, and imagine a scenario known as a dirty read. At time 1, transaction 1 updates a user's address. Then, at time 2, before transaction 1 has officially committed, transaction 2 comes along and reads that updated address. But wait, at time 3, transaction 1 hits an error, aborts, and rolls back its execution results. So look at what happens at time 4. Transaction 2 is left holding an address value that, mathematically and officially, never even existed. Just like that, our data is corrupted.
And honestly, dirty reads are just the tip of the iceberg. The SQL standard identifies several other really sneaky anomalies that can happen during the execution of concurrent transactions. You have non-repeatable reads, which is where you read the exact same row twice during a transaction, but you get different data because someone else updated it in between. Wild, right? And then you have phantom reads, where entirely new rows mysteriously appear or disappear from your search results simply because another transaction is inserting or deleting data in the background.
All of this brings us to one of the most fundamental system design trade-offs in computer science: isolation versus performance. Achieving perfect, serializable isolation completely prevents all these incomplete writes from propagating, which is absolutely fantastic for data safety. But the rigorous coordination and synchronization required to actually do that negatively impacts your overall throughput and performance. So if you lock everything down completely, your database is totally safe but heavily bottlenecked. It's a massive balancing act.
Part 2. Restoring order. Concurrency control and locks.
Let's quickly outline the three main approaches systems use to schedule and execute these concurrent transactions. First up is optimistic concurrency control, or OCC. It lets transactions execute without blocking, optimistically assuming conflicts will be rare, and it just checks for them right before it commits. Next is multi-version concurrency control, or MVCC. This clever technique uses timestamps to keep multiple versions of a record, which guarantees a transaction has a consistent view of the past without needing to lock anything. And finally, there's pessimistic concurrency control. This one assumes conflicts absolutely will happen and uses strict lock-based methods to restrict execution right from the start.
Let's zoom in on that pessimistic approach for a second. At the absolute center of it is a component called the lock manager. I really want you to think of the lock manager as the strict bouncer of our database system. It's a central control component that actively guards access to database resources, mathematically preventing concurrent requests from stepping on each other's toes and violating data integrity.
The lock manager generally hands out two distinct types of passes. First, you have shared locks. These allow multiple transactions to read a piece of data at the exact same time, mostly because concurrent reading is entirely safe. However, if a transaction actually wants to modify that data, it must request an exclusive lock. An exclusive lock can only be held by one transaction at a time, strictly forcing all other interested transactions to wait in line until the modification is complete.
So the crucial point here is how these locks are managed throughout a transaction's lifespan. The standard protocol for this is called two-phase locking, or 2PL. In this lock-based approach, a transaction acquires locks as it needs them, but it's required to maintain those locks on the records being modified until the entire transaction terminates and releases them all at once. This strict maintenance physically prevents any other transaction from swooping in and modifying those records mid-flight. But of course, this strict, rigid locking introduces a terrifying new complication. What exactly happens when two transactions are stubbornly waiting on each other, literally forever? Let's walk through this scenario step by step to see exactly how a pessimistic schedule can result in a system freezing deadlock. In step 1, transaction A takes an exclusive lock on record 1. In step 2, transaction B takes an exclusive lock on record 2. Okay, no problem so far. But now, in step 3, transaction A realizes it needs to update record 2 to finish its job, so it requests a lock and waits. And in step 4, transaction B realizes it needs record 1, so it requests a lock and waits. Boom! We are now in a circular wait. Neither can proceed because the other holds the key.
When this happens, obviously the system cannot just stay frozen. It triggers deadlock handling. The lock manager detects the circular wait and makes a brutal but completely necessary decision. It picks a victim. The manager forces one of the pending transactions to immediately abort, rolls back its execution, and frees up its locks. This effectively breaks the circle, allowing the surviving transaction to proceed, while the aborted one is instructed to just retry later.
It's truly fascinating to anchor all this theory in reality. For instance, massive systems like PostgreSQL and MySQL utilize advanced atomic commitment algorithms to handle these exact mechanics for distributed transactions. Then you have TIDB, which is a highly scalable, strongly consistent open-source database that leans really heavily on these concepts while remaining completely compatible with MySQL. And on a slightly different evolutionary branch, Apache Cassandra acts as an eventually consistent database, purposely relaxing some of those immediate isolation rules we talked about to achieve massive global availability.
Part 3. The final system view. Orchestrating the architecture.
Now, what's really interesting about this is how seamlessly this journey maps from a simple user click all the way down to safely committed data. A user initiates their logical unit of work. Immediately, the transaction manager takes the reins, coordinating and tracking every subsequent step. It consults the lock manager, which acts as the ultimate gatekeeper, checking status and granting those shared or exclusive locks. Once cleared, the database executes the actual read and write operations against the memory's page cache. And finally, the ultimate success, the commit, where changes are pushed, made permanently visible to others, and written durably onto the disk.
This is how databases stay correct under concurrency. It is an invisible, perfectly choreographed dance of transaction managers and lock guards firing millions of times a second. Without these elegant mechanics, the digital infrastructure we rely on every single day would completely collapse. But it leaves us with a fascinating question to ponder. As databases become increasingly globally distributed, spanning across multiple continents, how on earth do these systems maintain this perfect illusion of instantaneous isolation when data is literally limited by the speed of light? We'll see you next time.